Hey everybody, we're going to continue studying limits at the integers. I've just picked on the integers in this particular example, but we could actually just find the limits at any number. So just picking on the integers because it makes it a little bit easier. Hey, so to get started, let's do this. Let's consider the piecewise function given below, and let's sketch a graph. I've just noticed over the years that students need some extra practice with sketching a piecewise graph. So it might be in your best interest to kind of pause the video right now, and then over here in this area, perhaps you'll want to sketch a graph and then come back and check it. So why don't you go ahead and pause it, and then you can come back and check your work to see how you did. Alright, double checking your work, making sure that you have a linear piece right here that's closed on the left, open on the right. Up here, this linear piece is closed on the left, open on the right. Then we have the point ordered pair 2, 2. And then coming to this piece right here, we have open on the left and closed on the right. And then for the last piece, it is open on the left and closed on the right. However, this opening right here is actually the point that's there from the previous piece. Okay, so not a great graph, but hopefully enough for us to do our work with. All right, so we're going to come down here and we're going to consider looking at the limits at the integers. So let's first of all pick on the integer x equals 0. Okay, and if you could try and write neat, unlike me, again, like I said, I'm practicing trying to get better. Okay, let's consider at x equals 0 the limit. Okay, and what I want you to first notice is this, that there's no part of the graph to the left of 0. So really in this case we're only going to consider coming at x from the right. So we wouldn't want to say that the limit does not exist over here. There's no part of the graph to make that assumption from. So we're just going to really focus our attention on a right hand limit, since that's all we have is a graph to the right of x equals 0. Okay, so let's look at the notation. So the limit as x approaches 0 from the right. And it wouldn't be wrong to leave off the superscript here, but it's just a little more descriptive of the fact that we are considering coming at 0 from the right. So the limit of the function as x approaches 0 from the right. Now you could put in the notation f of x here, but I want to pay particularly close attention to the different pieces here. If I'm approaching 0 from the right, the graph is a great visual of which piece you're on. Well, approaching 0 from the right means you're on this piece right here, which happens to correlate to this top piece here in the equation. If we didn't have the graph to look at, if you kind of covered that up, if you were looking at just the equation and you're asked to evaluate the limit as x approaches 0 from the right, you want to think about values that are close to 0 but to the right of 0. And in that case, that would be something such as 0.1, 0.01, and you can kind of look in the piecewise function here in the domain, and you can see that values close to 0 to the right of 0, bigger than 0, would put you on this piece right here. So what we're going to do is choose the piece negative x plus 1. It might be better to put it in parentheses, but not necessary. All right, so what are our options? Well, look, we have a graph to look at. We can evaluate the limit as we approach 0 from the right from the graph, and notice that the y values are going into 1. Or simply, why don't we just get in the habit of trying direct substitution, also known as analytical method. Why don't we just get kind of in the habit of evaluating our function at 0 to see if we get a nice number, and we can move forward from there and go on to the next problem. Evaluating the function at 0 produces 1, and that confirms that that is actually the limit from the graphical approach. Okay. Because this graph doesn't have anything to the left, the only behavior we want to consider looking at is behavior to the right of 0. So at this point right here, we're finished, but let me just also make mention that it's okay to say, so let me kind of see if I can get this out. I don't know why it won't take it. Or, that is, or it would be totally acceptable to say the limit as x approaches 0 without a superscript of the function equals 1. All right, let's move on to the next integer. And again, like I said, we don't have to limit our look at our study of limits of the integers. It's just it was easier to graph that way if we were just dealing with integers. I mean, I could look at limits as x approaches non-integers, but this is just more convenient for us. Okay, let's now look at the limit as x approaches 1. Okay, and again, like we've discussed, is there a graph to the left and to the right of where x equals 1? Certainly there is, so we want to consider both the left-hand limit and the right-hand limit. So as you approach 1 from the left, let's kind of determine what piece we're on, and of course the visual here of the graph is going to help us quickly. If I'm approaching 1 from the left, I'm over here on the top piece, so I'm going to go ahead and choose negative x plus 1. Now, don't misunderstand. It's not wrong for you to just put the general notation f of x in here. You could have easily have done that. But we want to maybe try a direct substitution method first. So it would be good to put not f of x here, but the specific piece. Again, to evaluate this, as I approach 1 from the left, I can look at the graph and see that the y values are going into 0, or evaluate this piece at 1, and when you plug 1 in for x, you do get 0. Okay, so that's your left-hand limit. Okay, let's look at the right-hand limit. Okay, if I'm approaching 1 from the right, well, here's 1, go to the right of 1, but you want to come back to where x coordinates are 1, so we're on this piece right here, and this piece is actually, your second piece, your horizontal piece here. And so what's the limit now? Well, you could look at the y values, determine that they're all maintaining a constant height of 1, or you can look at the analytical approach of direct substitution and plug in 1 everywhere you see x, which is nowhere, so you know your answer is 1. And again, we could say that therefore, or we could say that this implies, when you look at the left-hand and right-hand values here, y values, they don't match up, so we say the limit does not exist. And the limit as x approaches 1 of this function now, and here you'd want to use f of x, just because if I approach 1 from both the left and the right, I'm on 2 different pieces here, so it's just better to use f of x notation here. This does not exist. And again, you could look up here and you can see that that's a jump discontinuity, something we've studied before, and that makes sense when you have a jump discontinuity that your limit's not going to exist there. Okay, let's look at the next integer at x equals 2. Okay, well, when you first look up here at x equals 2, the function does exist at 2. Its y value is 2, and the limit does exist as well. It's just not going to be 2. But if you were asked just to kind of quickly do an inspection, does the limit exist as x approaches 2 on this function? Certainly it does, and it's going to equal 1. But if you're asked to show the work that supports your answer, then you want to show both the left-hand and the right-hand limit. So we're going to do that right now at this time. Approaching 2 from the left. Well, again, here's 2. Approaching 2 from the left means you're on this piece. That's the second piece, and that's 1. And doing a direct sub in, we get 1. Approaching 2 from the right. Well, again, here's 2. From the right would put you on this piece. The piece that is defined between 2 and 3, so that would be this piece right here, x minus 1. Direct sub in, it works, you get a 1. Okay, and this implies that the limit exists, and it's 1. Okay. At x equals 3. Okay, well, let's first have an idea of what our answer should look like, and then we'll have the work that supports it. At x equals 3, it appears that the limit does exist, and the intended height is 2. So that should be our answer from the left and from the right. Okay, if we're approaching 3 from the left, that's smaller values than 3, So close to 3, but smaller values than 3. So that's going to put you on, you can either look at the pieces and where they're defined or look at the graph. Less than 3, put you on this piece. Numbers less than 3, like 2.9, that would fit in here. So x minus 1. Direct sub in, evaluate, get 2. Alright, let's look at the right-hand limit. Okay, if I'm approaching 3 from the right, okay, here's 3 from the right, here's 3 from the right, pardon me. 3 from the right would be between 3 and 4, so we're looking at the last piece. Direct sub in, evaluate at 3, you get 2. Oops. Ah. Okay, let me see if I can select this and take that off. Okay. Good. Okay, and one last limit at 4. Now notice that there's no graph to the right of 4, so we can only consider what's to the left of 4 a left-hand limit, if you will. It's called a one-sided limit because there's no graph over here. So, slip down here. And like at x equals 0, we're only going to have a left limit. It wouldn't be wrong to leave off the superscript, but it's just a little more descriptive if we leave it on. Okay, so what's the limit as x approaches 4 from the left? We'll run that last piece, and that last piece is negative x plus 5. You can either look at the graph or do a direct sub in, and we get an answer of 1. And there's nothing to conflict with it on the other side, so we're just finished. And like I said, back up there at x equals 0, or you can drop the superscript. So that's the limit there. Alright, so I just wanted to kind of review, revisit left-hand, right-hand limits, showing the work that leads to your answer. Now certainly unless you're asked, you don't need to show the left-hand and the right-hand limit, but this is going to help us with some work that we're going to do later. Again, like I said, you don't have to show all this. Alright, so that's it for this topic.